Okay, hello everyone. I'm Hongbo Mo from PhD student from Professor Linley's and Professor Julio's group, University of Manchester. I'm glad to share my work of laser-assisted modification of electron transport layer for ambient-processed perovskite solar cells. Yeah. So the talk includes 4 parts: the introduction of solar cells and the perovskite, and the results. Analysis of the laser-assisted modification of electron transport layer for perovskite solar cells, and the conclusions and related works. As we know that the energy crisis is global warming and are very urgent problems for human beings. However, the majority of energy production is still based on the fossil fuels, which made up around 84% of global energy production. And the carbon emissions from the fossil fuels is a major causes of global warming. Therefore, it is critical to develop renewable energies such as hydropower, wind, solar, and other renewable resources. So the solar PV is one of the most abundant natural resources that environment friendly and totally free. As we can see from the figure 2A, the solar panel installation capacity is increased rapidly from 2010 to 2030. By the 2030, the solar PV installation capacity will increase to up to 1,500 gigawatt energy. Therefore, there's still great potential for solar PVs. And from figure 2B, we can see that by 2050, the solar panel capacity will further increase all over the world, especially for North America, Europe, and Asian countries. So the perovskite solar cells are one of the most promising candidates for the new generation of solar technologies. Up to date, I record efficiency of around 25.7 efficiency have been achieved by the single conduction of perovskite solar cells. And for the silicon and perovskite tandem solar cells, 31.3 is achieved. So the perovskite is a classic materials that has a crystal structure of ABX3, where A site is organic and inorganic cation, and B site is metal elements like tin element and lead element and tin element, and X site is fulfilled by the halogen element like chloride and bromide and iodide. So the working process, the perovskite solar cells is sandwich structures contained of ITO, FTO, and electron transport layer, and perovskite materials and whole transport layer. And on the top is the metal electrode. So when the perovskite materials absorb the incident light from the sun radiation, the free electrons and whole pairs is generated within the perovskite materials. And the electrons will transfer from the conduction band of perovskite layers to the conduction band of the electron transport layer, eventually reach to the ITO and FTO, and the holes will be transferred from the valence band of the perovskite layer to the whole transport materials, and eventually to the metal electrode. So electricity are generated when it is collected to the outside equipment. So here I'm going to present our recent paper of laser-assisted ultra-fast fabrication of crystalline tantalum-doped titanium dioxide for high humidity processed perovskite solar cells, which is published in ACS Applied Materials Interface this year. As we can see from the figure 5A, represents the structure of the perovskite solar cells. It's a planar structures with ITO and compact titanium dioxide as ETL, and the perovskite as spiral and gold. So the Figure 5b shows the SEM cross-section view of actual devices, which are fabricated in ambient air. In this study, we try to dope tantalum element, TA element, into the titanium dioxide film to improve the electron transportability of the ETL. So first, we try to use a conventional furnace treatment to find out the optimized doping ratio of TA doped titanium dioxide. And we can see from figure 5D is that 3% concentration of TA elements for the titanium dioxide shows the best efficiency. And then after we found the optimized concentration, we're trying to use the laser treatment to fabricate a TA doped titanium dioxide with different laser treatment temperature. As we can see the figure 6b, that the thermal profile of the titanium dioxide when during the laser processing is recorded by a thermal camera. And figure 6c shows the actual thermal image during the laser processing. So first, we use the Raman measurement and XRD measurement and XPS measurement to investigate the change of crystallinity and surface chemistry for TA doped titanium dioxide prepared by the furnace and laser process. As we can see from the 7AB, the Raman spectrum shows that crystallinity is increased with the laser treatment, with the rise of the laser treatment temperature. As we can also see from the 7C, the XRD spectrum, we also can find that the peak intensity is also increased with the laser treatment temperature. So the XRD measurement is consistent with the Raman measurement. And the TA element is doped. To confirm TA elements doped into titanium dioxide, we carry out XPS, and we found that TA is doped into the titanium dioxide with the TA peaks observed from the XPS. And to study the surface, TA 3+ state, we calculated the ratio of TA 3+ to TA 4+, and we found with the laser treatment temperature increasing, the ratio is dropped. That means the surface defects is reduced, which is benefit for the perovskite solar cells performance. We also carry out the SEM measurement for the perovskite film deposited on the furnace and laser treated titanium dioxide film. As we can see, the laser treated sample doesn't show the obvious difference in terms of perovskite morphology, and all the perovskite films are fully covered and distribute uniformly. We then investigate the optoelectronic properties of the devices based on the furnace and laser-treated titanium dioxide. As we can see from figure 9a, the photoilluminescence, and figure 9b is a photon transient photoillumination, and figure 9c is a conductivity derived from the JV measurement for the titanium dioxide film and gold deposited on the top. And figure 9D shows the recombinant impedance measurement of the perovskite solar cells. So the PL and transient PL and also the impedance show that the surface show that the recommendation is suppressed by the laser treated titanium dioxide film. And from the conductivity measurement, we found that the laser treatment, the titanium dioxide by the laser treatment at 800 shows the highest conductivities. And then we measured the ITO resistance by the two-probe method the ITO measured. The ITO resistance is shown in the figure 10, and we can find that the laser treated processed ITO shows a lower resistance compared with the furnace treated at 500. That could be the reason that laser treated the perovskite solar cells based on the laser treated T8 doped titanium dioxide show better performance than the furnace. And we also found that with the laser treated temperature increasing, the resistance of ITO is also increased. That could be the reason why here the conductivities by the 800 shows better conductivity than the titanium dioxide at 900 degree because they measured by the titanium dioxide with ITO together. And then we measure the photo performance of the devices based on the laser treated titanium dioxide and furnace treated T8 titanium dioxide. We found that the performance based on the laser treated T8 titanium dioxide shows better photo performance than that of the laser treated titanium dioxide film. Is for the CS-FA PBI3 perovskite solar cells. The efficiency based on the laser treated T8 titanium dioxide increased from 17 to 18, and for the MA PBI3 perovskite solar cells, the efficiency increased from 15 to 16. And in conclusion, the advantage of laser assisted T8 titanium dioxide for electron transport layer of perovskite solar cells. The first is improve the crystallinity and conductivity of T8 titanium dioxide film. Also, the surface defect is positive by the laser treatment during the high temperature process. Also, the less thermal damage to ITO substrate means the less resistance of ITO substrate. And more important, the whole fabrication time for the laser-assisted method is within 25 seconds, compared with conventional furnace treatment around 30 minutes, as well as reducing the cooling time. And the efficiency is improved. So, after we fabricate the planar structure perovskite solar cells, we also use the laser-assisted fabrication method to fabricate the lithium-doped mesoporous titanium dioxide for the efficiency perovskite solar cells, and this work is in progress. As we can see that the laser process is repeated here. The first step is to sintering the mesoporous titanium dioxide film, and the second step will use a similar laser procedures to annealing to dope the lithium ion into the mesoporous titanium dioxide film. And we also found the similar results. The improved sintering property of mesoporous titanium dioxide film and the high efficiency is achieved of 19% based on the CSFA PBI3 compared with furnace of 18 efficiency. Also, the resistance, also the hysteresis is also reduced compared with the furnace treated lithium doped titanium dioxide. The fabrication time is also reduced from compared with furnace from the 50 seconds, 25 seconds for sintering and 55 seconds for doping process, compared with furnace of 30 minutes for sintering and 30 minutes for doping process. And apart from the laser treatment for the titanium dioxide, we also prepared use a laser processing of potassium bromide modified tin oxide for efficient, rigid, and flexible perovskite solar cells. And this paper is under review right now. So the efficiency of around 20.14% is achieved with potassium bromide modification for rigid perovskite solar cells. and which is at a similar level with the perovskite based on the hot plate treatment, tin oxide. Also, we found that, but it's a different story for the flexible solar cells. We found that the flexible solar cells based on the laser treatment exhibit around 17% by the laser process, compared with 15% by hot plate process. And the main reason is because of the minimal thermal damage to PN substrate during the laser processing, because it's a rapid scan processing and very fast cooling rate. Also, we measure the bonding performance of the flexible solar cells, and we found after 1,000 bonding cycles, the 80% of initial efficiency is returned, and compared with hot plate processed tin oxide on PN substrate of 40% of the same bonding test. So the laser processing has a great potential for the wide range of the application of perovskite solar cells. So in the future, we can also apply for the laser processing not only for the ETL, but also for the perovskite and whole transport layer. So that's all. Thank you.